So let's start with our research question here. The research question is, what is likely to occur if a new strain of influenza enter into a population of 100,000 susceptible? How will the average number of people who are susceptible, infectious, and immune will change during the following weeks? So we have a population of susceptible, meaning that none of them is immune. And we have one infectious person. Is infectious because he can contaminate or transmit infection on to other people. So we would like to see what would be the change in the population who are susceptible and among those who become infectious and immune. So let's assume that this is a closed population, like there are no entry, so no migration in, and no birth, so it's closed, and there are no migration outside, so, and no death, no one is dying. So this is just for understanding what may happen. So we have a closed population here. And let's also assume that if you become infectious, you will later become immune. And when you become immune, you're protected for all your life. So we have two assumptions here. So we have our first step here, it's our research question. So this is just for you to remember again. Susceptible is someone who's not infected, but who can potentially be infected if he's exposed, if he's in contact with someone who is infectious. Infected is someone who is infectious, who has the infectious agents, but he cannot transmit the infection to other people. Infectious is that you are infected, but you are also able to transmit the infection. Immune, it's simply that you're protected. But in our case here, we don't have infected. We just assume that once you become infected, you are also infectious. You can transmit. So we're trying to make it very simple here. As I say, we need to look at the literature. The source of the literature can be the research articles, gray literature, previous models of the same issues or similar issues. And you can organize it into different categories. For example, how long is the latent period of other forms of influenza, for example? How long is the infectious period? In our case, it's a new strain, but we want to see also other forms of influenza. What is the R0 of other forms of influenza? Does the infection affect all the age groups, or does it affect mostly children or adults? So you kind of really, as an investigator, try to see in details the common characteristics of the infections that is in the literature. So for example, in case of previous influenza cases, the latent period is about 1 to 2 days, and the infectious period is about 5 days, and R0 is about 1.5 to 3, meaning that the infectious can go on and on if no one is protected. So the third step is the model design. In the model design, there are some points to always keep in mind. The first is the natural history of the disease. The natural history is when a person is sick, and we try to see every steps how the disease evolves with no intervention, no medication, nothing. So we see what are the different stages of the disease. That's what we call the natural history of the disease. So every infectious disease have a particularly different natural history. For example, the incubation period is generally different depending on which infectious disease we're talking about here. So you need to know, to have an idea about the natural history of the infectious diseases that you are dealing with. And also the prediction period of the model. For example, if it's you want to make prediction over long term, for example, 2 or 5 years or 10 years, you will need to consider factors like birth, death rates, population migration, because it is likely to affect the characteristics of your population. So it's really important to consider the demographic parameters here. But for our research question, we really make it simple. There is no birth, there is no death, there is no population migration. And also your research question is a very important element to consider about the design. The same way when you're doing any kind of research in epidemiology or in public health, the type of research question that you have kind of tell you what kind of design you have to follow, cohort study or cross-sectional or qualitative research. So the same way here, your research question will tell you what kind of model structure you need to consider. There are many types of model structures. The simple one, for example, is SI, susceptible, infectious. So when you are susceptible, directly you become infectious. This is HIV. Generally, when you're susceptible, once you get infected, you become infectious. And you remain infectious until you die, or if we consider the natural history. But we have another one, SIS, susceptible, infectious, but the infectious can come back here to become susceptible. Those are cases of short curable sexual transmitted infection like chlamydia or gonococcal infection. If you have it, you become infectious. Once there is a treatment, you are cured, you become susceptible again. So it's like a circular movement here. We have the SIR, susceptible, infectious, removed. Removed here means you are maybe immune or maybe the person is dead. So that's in the mathematical notation, we say removed here because you are removed out of the system, out of their infectious dynamics. So we have, the next one is the SIRS, this one here. It's just the same one here, but you come back to the susceptible. If you are immune here, you remain here in case of SIR. But in case of SIRS, the removed can come back here. For some infections, you can lose your immunity over time. For example, some cases of mumps, people can lose their immunity and become again susceptible here. And then we have the SEIR and the SEIRS, same. The only difference here, just we have this stage here. Remember, I mentioned in the beginning that you are infected, but you cannot transmit the infection to other people. So this stage here, we don't have it in the SIR. But for our model structure, we will make it very simple. We are working with SIR, meaning that we have susceptible. Once you leave the susceptible box, you become infectious. So meaning that you can transmit the infection to other people. And the next step, you become, you are removed, you are immune forever. So our model for today is the SIR model. So this is our population. We're going to try to make some simulation here. Firstly, I just want you to see how people may move from different blocks here. We have 3 blocks, the blocks of susceptible, infectious, and removed here. We have our assumptions. Remember, we say we have permanent immunity. So if you become immune, you stay here forever. Closed population, there is no entry, no birth, no death, and no migration. And we assume that once you're infected, you become infectious directly. ST is the proportion of susceptible or number of susceptible at time T. Time can be 1 day, 2 days, in terms of days, or in terms of weeks, or in terms of year. So you need to decide about the time step you're using. So you want to talk, maybe for our case here, we're talking in terms of weeks, or we can make it even simpler in terms of days. But ST is the proportion of susceptible at time T. IT is the number or proportion of infectious at time T, and the same for removed, the proportion who are immune at time T. So what may happen? We started with one case here. He infected 2, and because they are infected, they move to the next box here, and 1 becomes immune. When you become immune, you have to move to the next box here. And we have 2 newly infected here. They were susceptible, they are now infected, so they have to move in the infectious box here. And we have 1 who got infected. He becomes immune, so he moves there. So if the time step is every day we're gonna see some migration of people from one block to another block. And this is what we try to simulate now. How can we estimate the number of people who will remain here over time? So if I come after 10 days, how many people will be here? And after 10 days, how many people will be here or here? So we can estimate that by using mathematical parameters and model to estimate how people change in each of the categories here. And all the migration is, we're gonna see that in coming slides, how to estimate for each of the block here. But before we get to that, we need to think about the methods. There are generally 2 big methods. We have what we call deterministic models. To make it very, very simple, deterministic model give you only 1 prediction. You have only 1 estimation here. It gives you on average what's happened. It will tell you, for example, on average, 2 susceptible becomes infectious every day. Or at average, 3 infectious become immune. So we have only 1 line of prediction. But for stochastic models, they introduce the notion of time and chance in the number of people moving from category to category. It gives you many scenarios that will tell you on average, for example, 10 to 13 people moves. So because we have a component of a stochastic component using chance here.